Hello, this is Boqing Gong from Google Research in Seattle. I will give a very brief tutorial on long-tailed visual recognition. I will start by this slide showing a very famous case in our computer vision community on ImageNet recognition. We have 1,000 classes we want to recognize, and by 2015, the machine learning models are already able to outperform human performance, as you can see here. It's really nice. It's a very significant moment in the community. But as we move forward, here I try to rank different datasets according to the number of classes in the datasets. And you can see very, very quickly, we ramp up the class of interest in the datasets. In NJUST, for example, here, we have more than 5,000 classes in the 17 version and more than 8,000 classes in the 18 version of the dataset. And the full ImageNet had more than 21,000 classes. The same happens in object detection or instance segmentation. The two curves roughly showed our useful ambition in the community that we want to recognize everything in our visual world. But as signified in this NJUST dataset, when we have a lot of classes of interest, many of them will appear in not the head, but the tail. We cannot collect enough of like hundreds of thousands of examples for those classes. We therefore need new hammers, new tools, new techniques, new models to achieve the ambition of recognizing everything. And that comes down why it's a good time to study the long-tailed visual recognition. In the next few slides, I will give a little more detailed examples about what I mean by this long-tailed visual recognition and why it's a good time now to study the problem. Still revisiting this NJUST dataset, the data actually is from the wild, meaning that with minimum human curation, we have more than 8,000 classes contributed by analysts from all around the globe to the dataset. So the data is from that community. It's pretty natural. And a lot of animals, wildflowers, they basically don't appear often enough, or maybe the number in the nature might be big, but actually it's very hard to capture by camera. So for all different reasons, actually a majority of the classes, they have less than 100 training examples for each of them. So it's a pretty long-tailed distribution. This is one. The second example is from Google. Some of my colleagues and Google Research compiled a landmark recognition dataset. And you can see in North America, in Europe, in East Asia, we got a lot of training examples of famous landmarks, but the other areas, it's very hard to get a lot of examples of those landmarks. Here, it's more like an instance retrieval or instance recognition problem because each landmark itself is a label in the dataset. So we have more than 200,000 different labels, and you can see, again, it's pretty long-tailed distribution. Third example is in face recognition. Researchers in Microsoft Research compiled a dataset about the celebrities. Okay, it's apparently some of the celebrities are not as popular as the others. So as a result, we cannot get enough training examples for actually a majority of the celebrities. And distribution over the identities, it becomes actually a long-tailed distribution. Another example is from this famous Elvis dataset for object detection and instance segmentation. It's not surprising because like the image on the left might be easy to get enough training examples, but the one on the right, as you can see, it's pretty boring. Not everyone wants to take a picture like this. So it's hard to get a lot of training examples, therefore, for the objects in this very boring scene. Naturally, the dataset itself, therefore, is also a long-tailed. It's long-tailed over the objects of interest. The list goes on and on like this dataset objects in the scene understanding dataset, or the image tagging. So all the different datasets, when we scale up the potential, the possible number labels, it turns out a majority of the labels actually will appear less frequently than the others. We got a long-tailed distribution. So as we move forward as a community, as we move forward, then we want to recognize more and more things by the machine models. The long-tailed distribution will naturally emerge. It's kind of like a challenge we have to tackle, we have to deal with. We cannot let it be the elephant in the room and ignore it. So this slide summarizes my personal view about this problem. I think it's a very timely topic, and it emerges whenever we want to grow the dataset or we want to grow the capability of the model, because the nature is, by nature, a lot of data, they have the long-tailed underlying distribution. If you are interested, you can try to get started on this problem by working like on the naturalist dataset for object recognition, or LV's dataset for object detection and incident segmentation. If you want to don't spend like too much computation at the beginning, and instead try to get a flavor about what this long-tailed problem is and what's the main challenge in the problem, what works and what does not work, I will recommend this ImageNet long-tailed dataset. It's a subset of ImageNet, and it has a subset which follows a long-tailed distribution over the classes. Okay, what about the tasks? It really depends on what you have been working on and trying to solve, because almost in all different tasks, when we scale them up, when we go to the belt, they have the long-tailed distribution. So it doesn't matter too much on which task you will work on. This tutorial will focus mainly on object recognition or classification. I will cover some of the representative techniques or methods in the field, but I believe many of those approaches are transferable to other tasks, such as the long-tailed retrieval, face recognition, object detection, instance segmentation, image tagging, and so on. We realized this long-tailed challenge and tried to compile it into decent-sized dataset, such that no matter they are in the research labs, in industry or academia, can all work on this dataset. So we have a medium-sized ImageNet long-tailed from this paper, and also for places recognition and face recognition, try to have coverage of different, slightly different tasks. And in the paper, we also have a memory bank-based approach, trying to kind of, enhance the tail classes by memory bank. So if you're interested, again, yes, I personally think this ImageNet IoT or long-tailed ImageNet is probably the best medium-sized dataset to get started with. And when you're working on this one, you might start to wonder, okay, what's the difference between this LTVR or long-tailed visual recognition and the imbalanced classification? Also, what's the difference from few-shot learning? I will try to explain using this figure. Imbalanced classification is a long-standing topic in data mining, machine learning, and computer vision. But I think I call it an old AI problem, because existing work in this space, they use data sets of like the first proportion of this long-tailed figure for the experiment. So indeed, different classes have different numbers of training examples, but the differences among them are not significant enough. Unlike the long-tailed distribution here, the one unique property here is that actually a majority of the classes appear in the tail. So that's different from the imbalanced classification. For few-shot learning, it's kind of like I call it a new AI problem because we try to transfer knowledge from like many shot learning data sets to the few-shot learning data sets. We can use meta-learning, transfer learning, zero-shot learning, external knowledge like attributes like NLP to help us solve this few-shot learning problem. This long-tailed problem naturally connects the dots between the two, and we are interested in solving the problem not only for many short classes but also few-shot learning classes, everything, the whole spectrum together. Another thing before we move on to some existing approaches is another view of understanding this LTVR. I think it's a domain adaptation problem because in domain adaptation, we have training examples from one distribution, but our objective is to make the model work well on the testing stage. Testing stage, however, the data comes from a slightly different distribution, so we call it target distribution. Why LTVR, or the long-tailed visual recognition, is a domain adaptation problem? It's because of our expectation. So the training set follows a long-tailed distribution over the classes, but we want the model to work well over all classes, right? Ideally, uniformly well on all classes. So there is a mismatch between what the model can see from the training set and what our expectation is about the model. So the mismatch also sometimes we create artificially, of course, balanced testing data set to challenge the model. In the real world, when the training set is long-tailed, very likely the testing data also follows the long-tailed distribution, but we still expect the model to perform well on all classes uniformly. So when we develop the model, we create sometimes a uniform, balanced testing set. So the mismatch creates a very interesting domain adaptation problem. We summarized this view in this paper published last year. And also from this domain adaptation perspective, we actually motivated a meta-learning approach to solve this problem, which I will cover later on. Okay, some popular methods to this problem. Before we cover any kind of like fancy techniques specialized for the long-tailed visual recognition, I want to spend some time to emphasize that because almost in all existing models, we use deep learning models to solve this problem. It turns out it's really important to warm up the model. To warm up the model, just do traditional supervised training using vanilla SGD, cross entropy, for example, and uniform sampling. You do not apply any of the fancy techniques yet when you warm up the network. This step, so far, in almost every existing, not all, but almost every existing paper I read, they have this warm-up stage. Here, I will explain a little bit more and show you some of the examples. So in this IJCAI paper published last year, authors found out that if you can pre-train the model representations, basically the neural network architecture before the last classification layer, by the existing vanilla instance-based sampling, it's possible to achieve strong long-tailed recognition ability by adjusting only the classifier in the second stage. So it's a two-stage approach. Stage 1, warm up the network by traditional cross-entropy learning. Stage 2, just freeze the first few layers, remove the classification layer, relearn the classifier instead. In the paper we published also last year on CVPR as a meta-learning approach, turns out actually in the full algorithm and beginning, it's really important to warm up the network. Without this stage, it does not work really well. As you can see with sample mini bench, we compute the cross-entropy loss. We update the weight by the parameter here, by the gradient here. So it's very traditional cross-entropy supervised learning approach to warm up the network. The same thing happened in this paper, I believe published ECCV also last year. So they have two stages. In the first stage, they use all images in the dataset to learn the feature subnetwork and the base classifier. So again, here the warm-up is by the vanilla supervised learning. So given the importance of this warming up stage, you may wonder, okay, maybe we can warm up not only by the supervised learning, but also some other techniques. Indeed, there are some other approaches to this. So this is paper we put on archive. So in stage 1, we warm up not one network, but actually an ensemble of networks. Will give us a little bit more comprehensive and complementary representations about the data. Therefore, in the second stage, we can better leverage the complementary feature representations to learn a good model. And some researchers from MIT showed that in addition to supervised learning, actually it's beneficial to warm up the networks by self-supervised learning. It's really nice because we can do this by not only using the labeled training set, but some unlabeled but related dataset to warm up the network. And they showed really improvements by warming up the network in this way. All the previous works we reviewed, they have a very clear boundary between the two stages. Stage 1, warm up. Stage 2, your fancy techniques to specialized for the long-tailed visual recognition. Interestingly, in the paper shown up here, the two stages are not kind of like, there is no clear boundary between the two. Instead, they are using annealing factor to smoothly connecting the two. So the annealing factor changes over time, over different epochs. Therefore, at the beginning, still we warm up the network. And stage 2, gradually, we have some rebalancing techniques to specialize, to tailor for the long-tailed visual recognition problem. Why warming up the network is so important? Because on the first kind of glance, you may wonder it's bad because by warming up the network using traditional supervised learning, for example, we bias the network to the head classes. We ignore some of the tail classes. It's kind of like counterintuitive. Why does it still help? Maybe because the long-tailed visual recognition is still a representation learning problem. If we got really good representations, we classify even some vanilla naive simple classifier could still do the job. So in the warming up stage, we are trying to learn visual representations that are good enough and transferable across different classes. So that's one view. Another view is like we are reducing the search space to the part that produces sensible output. Because the network with so many millions of parameters, the search space is huge. So we can feed the network some examples such that the network knows, okay, this region or this part of the search space is good. for the network to achieve small training loss. So that actually drives the network to a smaller region of the search space. It reduces that. Therefore, the second stage is easier to learn because we don't need to explore the full search space anymore. A third potential benefit of the warming up stage is that it opens up the door to unlabeled related datasets by using self-supervised or semi-supervised learning approaches. Of course, it's not perfect. There are a lot of hyperparameters now you need to tune for the warm-up stage, but because it's only a warm-up for the second stage, the two kind of decoupled, then what's the good stopping criteria, right, for the first stage? Also, what are the good validation data or validation accuracy for you to choose the learning rate and so on and so forth in the first stage? So there are some questions still need to be answered in the warming up stage. And okay, so that's about the warm up. So after you warm up the network, next, you can try to apply some sensible and sometimes some straightforward approaches could actually work. So I will review some existing popular, pretty fancy techniques for the long-tailed visual recognition, beginning with the weighting scheme. As I said earlier, the long-tailed visual recognition can be understood as a domain adaptation problem, and this view can exactly motivate us to design some weighting techniques. Let me show you why. So our objective is to have a classifier that works well on classes, meaning that the expectation here, we will have a uniform distribution over the classes. We don't see the testing data, so we have to replace that by the distribution of the training set, which is long-tailed. So putting PS here, we have to put PS here as well. Just do a little bit rewriting of the second term. We got something like a marginal distribution over the classes and the conditional distribution of the images given the classes for both the target distribution and the source distribution. Okay, we use omega y to denote this ratio here between the marginal distributions of the classes, and we use 1 plus epsilon to denote the ratio between the two conditional distributions. Let's look at the very end example here, because the procedure we can ignore and talk to me if you want to learn a little bit more on that procedure. The final example is something like this. Very, very naturally, we got a weighting algorithm for learning the long-tailed from the long-tailed distribution. Because without the weighting omega y and 1 plus epsilon, the first part is essentially a cross-entropy loss. But now we have to design the weights for omega y and epsilon. Interestingly, most existing works, they assume epsilon is 0. So the weight is over the classes. So very interesting, I'm not sure why still, but it works. In a lot of datasets, you can try this baseline first. Somehow it actually works fairly well. Ny is the number of examples in class Y. And you can design this omega y by the inverse of the square root of this ny. Roughly, it means that the weighting function should be a decreasing function of the class size. If you have a lot of class examples in the class, the weight should be small. So you promote the loss over the tail classes. This weighting scheme works fairly well as a strong baseline, highly recommended. You can also do kind of implicit weighting. You can oversample the tail classes such that the number of examples roughly match the number of examples in the head classes. You can, of course, also unsample the head classes. They kind of play on the implicit weighting scheme for this long-tailed recognition problem. Another interesting weighting function was proposed by Yin and co-authors. Yin right now is my co-worker at Google. So they introduced a concept called effective numbers. So the effective numbers of different classes, they have one hyperparameter beta. Again, you can see the weighting function is a decreasing function of the class size ny. And so on and so forth. The list goes on. I will not go through them one by one, but all the approaches so far on the weighting, they assume that epsilon is 0. It's not entirely true because that assumption sometimes can fail. So we therefore, in the CVPR paper last year, we tried to explicitly learn epsilon by a left-out development set. So it becomes a meta-learning approach. So we use the development set to learn epsilon. After that, we update the model using the training set. Why is this necessary? Because when we assume epsilon is 0, probably it's fine for the head classes, because we see a lot of examples of those classes. So given cat category, suppose this is a head class, because we can collect a lot of cat images, right? This conditional distribution between training and testing, probably they are roughly the same, because you see a lot of cat images. So it's fine. This ratio is probably 1, meaning that epsilon is 0. But for few short learning classes, you really cannot see a lot of training examples. So even though you see some of the images of our tail class, still it's not representative enough of the real conditional distribution of the tail class. So they are not the same. Epsilon, therefore, being 0 is not reasonable. We therefore want to learn epsilon, especially for the tail classes. Okay, so that's one weighting here. That's one set of existing approaches for long-tailed visual recognition. And the imbalance of our losses is another set of very active area with another set of popular and effective techniques. I will not go through the details here one by one. In the slide, I will attach the long-tailed BIP file. So if you're interested in those imbalance of our loss functions, you can search for the keywords. You will be able to see the corresponding papers. Some of them come from the face recognition community, because very naturally, when we have a lot of identities we want to recognize, they follow long-tailed distribution. Because of the time, we have to be a little bit brief. So this comes to actually already the last aspect of our last set of techniques for LTVR. I call them knowledge transfer, because we could have a lot of useful insights from the many short classes in the head. And some of those insights will help us learn from the tail classes. The key here is how to transfer the insights, or how to represent the insights in terms of transferable knowledge. In this paper, the knowledge is essentially a meta model that predicts the many short model parameters from few short parameters. As you can see, we can actually artificially create some training examples using the many short learning classes. So in the head, some of the classes we have enough training examples. We can resample to artificially create some few short learning scenarios. We learn the model from the full set of a lot of training examples for each class. We can also learn the model. So between the two, we can learn, therefore, a regression network That's the meta model. The basic assumption here is that that meta model is shared by the tail classes as well. So that's one. In this paper, the knowledge transferable from the head to the tail is not the meta model anymore. Instead, they become the samples or augmenting methods. So the idea is to augment the infrequent classes by translating and modifying some of the samples, like images, from the frequent examples, frequent classes. So you got some a lot of training images from the head classes and not enough from the tail classes, but learning and translation or modifying function from the head such that we can modify the examples or augment the examples from the tail classes such that we have a little bit more training examples for the tail. This one is, I personally find it very, very interesting. They are transferring the class geometry from popular classes to the few-shot classes. And you can see here on the for the classes with a lot of training examples, you can roughly get a class geometry in the classification space, fairly reliably, fairly high quality. The basic assumption here is that geometry should be shared by different classes, including the tail class. So they transfer that geometry from head to tail. Another paper here is feature augmentation. The knowledge transferred from head to tail, basically the class generic features. So the features assume that, okay, some of the features are shared by the head and tail classes, and some other features are unique to certain classes. So the class generic features, therefore, is assumed that they are assumed that are transferable from the head to the tail. Okay, yeah, that's roughly all about this last set of popular approaches to long-tailed visual recognition. At the very end, I want to recommend two interesting papers. One is the long-tailed classification by keeping the good and removing the bad momentum causal effects. So it's an interesting paper. It tried to understand the long-tailed visual recognition from a causality perspective, and correspondingly, they designed an approach. Another paper is also very interesting. It's not for the long-tailed visual recognition per se, but it's more like trying to explain when and how the network will memorize when they learn from the data. Especially when the data set is long-tailed, then they have to memorize the examples in the tail in order to achieve good generalization. So very, very interesting papers to me. Hopefully you will also find them interesting. To summarize, this long-tailed visual recognition is really a timely topic. As we, at least for me, working on visual recognition for many years, I want to see a day that we can have a machine model that's able to recognize millions of thousands of millions of objects, classes, instances, face identities from our visual world. So in order to achieve that, we have to work with this long-tailed visual recognition. We have to try to solve the problem in all different tasks, like recognition, detection, segmentation, tagging, and so on and so forth. So far, existing approaches, they have to warm up the deep networks in order to get good representation before we have some other specialized techniques for the long-tailed distribution. Not all existing papers, but I think most of the existing papers, they have to warm up the network. So it's an interesting perspective here. This stage, I think it desires a little bit more research, like how to warm up, how to tune the parameters, or how to actually get rid of this warm up stage. And in the second stage, we have some weighting techniques, we have knowledge transfer, we have head-to-tail knowledge transfer, and so on and so forth. A lot of very interesting methods happening in the second stage. At the very end, I want to emphasize again that when you understand this long-tailed visual recognition as a domain adaptation problem, it's actually not only a new understanding, but also it opens up a lot of opportunities because there are a lot of domain adaptation methods which can potentially benefit this long-tailed visual recognition problem. I want to give some final remarks to conclude the tutorial. First of all the opinions are mine, belong to myself. And secondly, the tutorial is not comprehensive by any means. We explained some intuitive ideas, but not the exact techniques step by step. If you are interested still, please go read the papers. We focused on long-tailed object recognition or classification, but I believe many of the techniques should be transferable to long-tailed retrieval, face recognition, detection, segmentation, tagging, and so on and so forth. When you check the papers, you will find out that actually some of the papers are still under review. They are on archive, but not being peer-reviewed yet. Please use your best judgment. Okay, thank you all.